Hello guys, welcome back to our last example in our lesson where we're talking about double integrals of polar coordinates, polar equations. And so the question here is asking us to find the volume of the solid that is bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. So the xy plane is pretty standard here. It's going to be at the base of our function, right? And that's where you guys can see that this portion is actually lying on that. And so the first thing that we want to do here is just go ahead and get our equation. This is what we're going to be integrating, right? This is the function we want to integrate into polar coordinates. So we have actually done this many times before that I can pull out a negative and we get our standard x squared plus y squared. I've talked about this in previous videos, that our equation that we're going to use here is z is equal to 4 minus r squared. So this is what we're actually going to be integrating. So now we want to talk about the bounds. So what our bounds are going to be. So the first thing is we're going to look at what theta is. So theta is going to be starting at the x-axis, right? So we're looking, and again, if you guys want to think about it in the visual right here, where this is the x and y, so we're looking down on it. So we're starting here at 0, and then we're just going to the y-axis, right? So our graph is going to go to the y-axis, which is going to end up being pi over 2. So this is the pi over 2 part of our graph, and this is 0. And then our radius is going to be, well, let's look at what we're doing with our problem here. So our radius is, so starting here at z, right? So at z, the radius is actually going to be 0. We're at the pole, so it's 0. And then we want to figure out what the radius is right here. So starting here, it's at 0, and we want to figure out what that distance is. Well, remember, guys, that z at this value right here is always going to be 0. So we can go ahead and replace z with 0, and we're going to get that the upper bound, the furthest our radius, the largest our radius is going to be here, is going to be at 2. So our radius is going to be at 2. So with that, it's ready for us to go ahead and start to set everything up. So we're going to go ahead and integrate from 0 to pi over 2. And then our radius is going to be from 0 to 2. We're going to go ahead and take the function that we're actually integrating here, which is going to be 4 minus r squared. And then we're going to do our dA, which is our r dr d theta. And that's pretty much it. So next thing we're going to do here is just do a little housekeeping. Let's go ahead and clean things up a little bit here. So actually, let's just do it right here. It's 4r minus r cubed, right? Let's just do that. So we can just go ahead and integrate that. So 4r minus r cubed. So the integration of 4r is going to be 4r squared over 2. And then the integration of r cubed is r to the 4th over 4. And we're going to evaluate that from 0 to 2 and then add on our d theta. So when we start plugging in our numbers, let's do this. We get the integration from 0 to pi over 2. When we plug in 2 here, we get 2 squared is 4 times 4 is 16 divided by 2 is going to be 8 minus 2 to the 4th is 16. 16 divided by 4 is going to end up being 4. And we plug in 0, we get 0. So we're going to get 8 minus 4 d theta, which is pretty awesome because we love these kind of integrals because it's really easy to do after this. I think the hardest part really is just setting stuff up, right? The integration part of it, other than the last video that we just did, that was pretty intense, but these are pretty straightforward, and they usually should be, right? These should be pretty easy stuff. The calculus that I want you guys to know is not this integration part. It's just really how to set up the integrals themselves. So if you got the blue right here, then we're good. So anyways, back to the problem. We subtract 8 minus 4, we get 4, and we're going to now integrate from 0 to 2. So we're going to integrate 4, which is just 4 theta, and we're going to go from 0 to pi over 2. So all we have to do, friends, to finish this problem up is plug in pi over 2 to our theta. When we plug in 0, obviously it becomes 0. So our answer here is going to be a lovely, wonderful, magical number of 2 pi. So this is going to conclude our lesson on polars and double integrals of polar functions. So I will see you guys in our very next lesson. So have a good one.